I think it is time to start. Let's start off, first of all, any questions from last time? DepthFirst Search, homework problems, anything like that? Okay. So what I'd like to start with is the problem of the day. Again, we started talking about DepthFirst Search, and the problem of the day is going to be about DepthFirst Search. But I want to cut ahead a couple of slides just to clarify, to make sure we understand what the issue is about. Last class we started talking about BFS. Along the way, it's going to be visiting and discovering new edges. Okay? When an edge discovers a vertex that had never been seen before, that is what we call a tree edge. Okay? When in the course, again, if you think about what's happening with every edge can be visited two ways. If it's an undirected graph, edge xy could be visited first time when you explore x. It could be explored first time when you visit y. And we're going to give each edge a label depending upon what happens the first time it was viewed. Okay? A tree edge is the first time if it discovers a new vertex. Okay, remember your search is starting from some vertex that was discovered but not completely processed. If that edge discovers a new vertex, it's a tree edge. If when we visit, the first time we look at an edge, it discovers somebody who is it discovers a vertex that is a descendant. Okay? Okay? If the edge goes to a vertex that's a descendant, that's kind of a forward edge. If an edge goes to a vertex that is that goes to a, what you call it? It goes to an ancestor, that's something we call a back edge. And if it goes to somebody that's not a ancestor or descendant, or involved with discovery, we call that a cross edge. Okay? So the important thing here is to realize that DepthFirst Search is a property. As you start a DepthFirst Search from a particular graph, from a particular node, it's going to discover every edge once, and when that edge is either going to be a tree edge, meaning it discovered a vertex, or it could conceivably go to some edge that is kind of already a descendant of it. Okay? To go to some vertex that's a descendant. Or it could go back to an ancestor. Or it could go to someone that's neither an ancestor or a descendant. That's a cross edge. Okay? So the problem of the day is going to be about properties of DepthFirst Search, and what did the edges look like? Let me see if I can go bunk, and let me try to erase this thing. So the daily problem that I know was saying that in a DepthFirst Search on an undirected graph, every edge is either a tree edge or a cross edge. What does that mean? Let's say that this is my BFS tree of discovery at some point. Okay? Let's say I'll have it look like this. Is it possible that when I explore, let's say this vertex, which is the last one that I'm exploring, I'm looking at its outgoing edges. Is it possible that this edge goes to its grandparent? Why or why not? You kind of get this idea? We're having a DepthFirst Search process unfold. How did it probably unfold? Well, if I'm looking at how it unfolded here, I started from this vertex, I explored this, I discovered this, I discovered this, the next vertex to explore was this, and then the next vertex on the queue was this, and then as I look at the outgoing edge, They look at the outgoing edges from here, nothing, nothing, nothing. Outgoing edge to here, it goes to my grandparent. Is that possible? You're shaking your head saying no. Why isn't that possible? Because this vertex, if we number these vertices 1, 2, 3, 4, 5, 6, 7, if it was an undirected graph where there was an edge 1, 7, what would the breadth-first search tree look like if we had started from vertex 1? We would have had 1, 2, 3, 4, 7. And then, trouble. Does everybody kind of see this thing? That there would have been an edge when we explored 3. Okay, what would have happened when we explored 3? Okay, again, remember what the process is. We would have discovered 2 and 3 and 4 and 5. What would have happened when we expanded vertex 3? Vertex 3 would have done this edge. Does everybody kind of see that? There's an edge 3, 7. When would we have discovered that edge 3, 7? It would have happened when we expanded 3. And this is what the depth first search of this tree would have looked like. Any questions? Does everybody see that the edge 3, 7 goes neither to an ancestor or a descendant? It goes to a brother, okay? Could go to a cousin, okay? I don't know how you want to label it. But it's not going to an ancestor or a descendant. And the reason is because of what breadth-first search does. It can't go to in an undirected graph. Can't go to an ancestor or a descendant. Because if there was an edge that went to an ancestor or descendant, we would have for the first time seen it when we had expanded the ancestor. And the tree would not have looked like that. The tree would have looked like this. Any questions about that? Yes? In a directed graph, all bets are off. If it was really a directed edge, then what would have happened? If there was an edge from 7 to 1 and we're starting to explore from vertex 1, would we see that edge 7 on 1's adjacency list? We would not, right? So the word undirected here is a big word, right? Okay, any questions? I'm going to talk today about some of the beautiful behavior of graphs in depth-first search, okay? Again, some of that goes away when you start talking about directed graphs. Because in a directed graph, there's only one way to visit the edge. And what happens with that edge happens with that edge. The important thing about breadth-first search and depth-first search is that on undirected graphs, they organize the edges in very restricted ways. Any questions? Can there be in a breadth-first search tree, we have a cross edge. Could we have a cross edge that goes from a younger brother to an older brother? Okay? Yeah? No, because if it was an undirected graph, the older brother was the one that got expanded first, right? So the edge would have gone that way. Okay? We would have discovered that edge when we were exploring 2 and not 7. So we can't have edges go to older and brother. Could we have an edge go from a node of, let's say, height 1 to a node of height 2? Would this be legal? Let me try getting black here. Suppose we have 7, 5. Is it possible to have a cross edge that looks like that? Certainly. 5 was discovered when 2 was explored, right? But the first time we would have seen this edge is when 7 expanded its children. Does everybody see that? Could we have an edge go back to a higher level? Could we have had a cross edge like this? Would that have been possible in an undirected graph? Yeah? I see an arm up. That may have been just a stretch. Is this possible? Yes or no? Somebody, yes or no? Preferably somebody who's not the same yes or no's as always. Which way, yes or no? No, because again, this could have been exposed then. So does everybody kind of see this, that the nature, if you have an undirected graph and you do a breadth-first search from it, okay, every edge will either be a tree edge or it will be a cross edge. And the cross edges are going to have very restrictive conditions on them. They can go from me to the lower level, they can't go from me to a higher level. Okay? They can't go from me to two lower levels down. Okay? And it should be clear that that's a result of the breadth-first search process. Any questions about that? Graph traversal is one of these things that some things in this class are going to sound easy and be hard. Some things are going to sound hard and be easy. Okay? Graph traversal is one of these things that I think sounds easy, but it is hard. Okay? Because there is more subtlety here about what is actually happening. Does everybody see that there's a structure imposed by the nature of the algorithm? And certain things can happen and certain things can't happen. Any questions? Okay. If that's true, let's continue. Let's go back actually to the last couple of slides from the previous class about breadth-first search. Because again, doing a breadth-first search for itself sake we don't do. But there are applications of doing breadth-first search and depth-first search as a building block to build interesting algorithms. One very interesting problem on graphs is something called the vertex coloring problem. The vertex coloring problem asks, is there a way to color the vertices with the fewest number, find a way to color the vertices with the fewest number of colors possible, such that no edge goes between vertices of the same color. Okay? And vertex coloring is a important problem in a lot of scheduling applications, a lot of different things. And once you learn to think in terms of coloring, it's a useful thing. But what about a world where we'd like to know if there is a graph that can be colored with 2 colors? Okay, we call a graph that can be colored with 2 colors bipartite. Bipartite means 2 parts, right? Bipartite. Suppose we have a world where there are, I'll call them, for now, just call them white vertices and black vertices. And every edge went between a white and a black vertex. That is a bipartite graph. Okay? Can anybody think in their lives of any time that they've encountered a bipartite graph? A graph where you can break the vertices into 2 sets and all the edges span that set. Yeah? Students and what? Teachers. Students and teachers. You could imagine a world where that there are teachers who put knowledge out and students that take knowledge in, but teachers reach the point where they don't want to gain any more knowledge. Okay? So every edge in a class, every professor has students that are taking it as their class. There is a difference between students and teachers, okay? But it naturally defines a two-partite graph. Half the nodes in the, some of the nodes in the graph are teachers, some of the nodes are students, and naturally, okay, edges can only go between students and teachers, okay? In a lot of different applications, you end up getting, bipartite graphs. And it turns out that algorithmically, some things are easier to do on bipartite graphs than other things. So if you see a bipartite graph, if you know it's bipartite, you got to win. But how can you tell whether a graph can be two-colored? How can we, given a graph, how could we tell that there's a way to separate the vertices into white and black, okay? Or red and green, or whatever two colors you want, okay? The idea is, what if we start from one vertex, okay? If this vertex is going to be white, okay, all of its neighbors have to be black. If this vertex is black, all of its neighbors have to be white, okay? If there was a contradiction, like let's say a graph like this, if I color this vertex white, that means that this vertex has to be black and this vertex has to be black. But note that I've now created a problem. That edge goes between two black vertices as opposed to two of different colors. Okay? It should be clear that for the special case of two colors, can a graph be two-colored? Basically, we can color it all, start coloring it one color, walk through the graph. Every edge is either going to go to an edge of a different color or it's going to go to an uncolored vertex, in which case I'd better color it differently than you're coloring me. And this is an algorithm to two-color a vertex. So let's take a look at this as an application of DepthFirst Search, breadth first search. How does it work? Okay, how do we two-color a graph? Well, we start out by declaring every vertex is uncolored. Okay? We're going to assume there's a way to two-color the graph until we get a contradiction. We're then going to do a breadth first search starting from the first vertex. The first vertex, if it's not been discovered yet, that means we haven't given it a color. Let's color it white, okay, and then do a breadth first search to color everything that is reachable from it. That's what this is doing. What is the action within the search? Here we got to take a look at what we do when we visit an edge or visit a vertex. Okay? Whenever we visit an edge, process edge, remember it was going to be called the first time we visit edge XY. If we visit edge XY, what are we going to check? If the color of X is the same as the color of Y, we've got a problem. Okay? Then there's a contradiction and it's not bipartite. Otherwise, color Y the opposite color of X. Okay? We could have checked whether if Y is uncolored. Okay? But it turns out that test isn't really necessary. There's nothing wrong with painting the vertex black twice. Okay? Any questions about that? What is the complement? Well, if the color is white, return black. If the color is black, return white. Okay? Any question? So we're going to color each, this loop is going to go through, color each connected component. That this should look a lot like the connected component algorithm, right? For each vertex, if it hasn't been discovered, it's a new component. Let's color it. I'll arbitrarily decide the first vertex is white, and then color it through. Any questions about that? About how this thing does two coloring? What you should see is this algorithm is not that complicated. Basically what it's doing is every time it visits an edge the first time, okay, it does something. Okay, and the breadth-first search enables us to systematically do that in a way that makes sense. Any questions? What is the running time of this algorithm? Okay, let's go back to the algorithm here. What is the running time of this algorithm? To color all, you've got an n vertex graph, m edges in the graph. What is the running time here? Ideally someone else. Anyone? Yeah? N plus m. And why is it n plus m? Each edge at most twice. Okay? Basically, that's what we're doing here. What am I doing when I visit an edge? This is a constant amount of work every time I visit the edge. Is that right? I'm going to do a test. I'm going to set a color. It's a constant amount of work. And I'm going to do this. The breadth-first search is going to insist I visit every edge once, every edge twice, and every vertex once. That's going to make it n plus m. Any questions? Okay, this is a good representative of a nice, simple breadth-first search-based algorithm. Any questions? Okay. Let's come back here. That's interesting. Let's continue on and talk now about depth-first search. Okay? Depth-first search is, remember, what did we say about breadth-first search? We were going to start from a vertex, walk over all the edges. We were going to, in a systematic way, and we were going to store the work that we needed still to be done on a queue. Depth-first search is we're going to do the same thing except replacing the queue with a stack. Remember, stacks had the property that they were last in, first out. Queues had the property that they were first in, first out. So if we think about what's going to happen on a breadth-first search, you start from a node in a BFS, you're going to kind of wander around and slowly grow out in that network. That's what a BFS, a breadth-first search is going to look like, right? What is a depth-first search going to look like in a graph? You're going to go, discover a new vertex. Once I discover that new vertex, what am I going to do? I'm immediately going to go try to discover another vertex, try to discover another, try to discover another. In depth-first search, I'm going to wander probably pretty far away from my starting point pretty quickly. Because the one thing I'm going to explain, the next thing I process is going to be the last vertex that I discovered. And the moment I discover something new, I'm going to suspend my attention and go look at that. Any questions about that? Here is a recursive implementation of depth-first search. And I want you to look at this pretty carefully. Okay, let's blow this away. What does depth-first search do? We are given a graph and a starting vertex. Okay? What are we going to do? The important point here is we're going to start visiting this graph V, the vertex V. If we want a first chance to visit V, the moment we discover it, let's do a processing. That's cargo associated with it. More generally, what is the real step that's going on? We're going to get P is going to point to the edges of vertex V. We're going to look at the edges coming out of V. If this list of edges is null, we have finished processing that vertex, okay? And We're going to go over to here, and in fact, again, if we take a look at the bottom, we're going to say that that vertex is finished processing. Okay, actually, let's come back here. But in general, what are we going to say? If P is our list of edges, Y is going to be the next vertex that we're connected to V. Remember, we're going through V's outgoing edges in its adjacency list. Suppose the next edge we're considering is Vy. That's really what this is saying. If Y has not been discovered, what does that mean? This edge Vy discovered Y. That's great. So what are we going to do? The parent of Y is V, because V discovered Y. We're going to process that edge, Vy, okay, because we just discovered this edge for the first time. And we're then going to do a recursive call, doing our depth first search continuing from vertex Y. The moment it's discovered, we're going to make a recursive call, interrupt what we're doing, and keep going exploring from there. Okay? And again, this is a recursive call. If we take a look, let me clear the screen again. I know I wish I could fit this on one slide, but it's not much more than one slide. See here, depth first search is making a recursive call to depth first search. Okay, this is a recursive algorithm. Stacks are recursive things. Okay? I mean, you know that when you're doing recursion, basically you store the records, the interrupted things on a stack. Finish doing what you're doing and then pop it off and go to the next oldest thing. That's kind of what we're going to do in depth first search. Any questions about that? And then we're going to process depth first search, process Y. Once we finish processing vertex Y, we're going to keep looping through, okay, all the edges associated with vertex V. Maybe we'll discover something new. Maybe these vertices would have been discovered. But we're going to keep doing that. Once we're done with that, if we want to process V at the end of the process, we can do it. But the important thing is that now we say that that vertex V, we've checked out all of its outgoing edges. It's completely processed. Any questions about that? Okay. Let me do a quick example here. There's a little more complicatedness. But what is interesting about depth first search? Depth first search organizes the edges of an undirected graph in a kind of amazing way. Okay? Namely, I'll give you the hint right now. Okay? Every edge is going to either be a tree edge or a back edge, back to an ancestor. Okay? What happens if we do a depth first search from V? Okay, from vertex 1. We're going to maintain a stack of what vertices need to be processed. Okay? Let's say we're starting on vertex 1. Okay? Now what are we going to do? We look at the outgoing edges from V, and suddenly we discover vertex 2. Vertex 2 has been discovered. We're now going to resume, basically put V1 on the stack and now work from vertex 2 and explore it. Does everybody see what we did? We created, that edge. From vertex 2, we're going to look at its outgoing edges. And let's say the first one was 3. Ka-chunk, we're going to interrupt working on 2. And now we have discovered 3. From 3, we're going to look at our outgoing edges. And 4, ka-chunk, we discovered 4. Put that on the stack. Let's explore 4. 4 is adjacent to what? 3, but 3 has already been discovered. Okay? 5. No one has discovered 5. I just discovered 5. Now let's do my search. From 5, I could go divert to edge 2, but 2 has already been discovered. It's not completely finished yet, right? Now, from 2, so what's that edge going to be? That's an edge from 5 back to 2. See those dotted edges there? That's a back edge. It's going back to an ancestor. Now I take a look at what else would I find. Oh, 6. 6 is new. Okay? I'm going to put 6 on my stack. I look at the outgoing edges. 5. Well, 5's been discovered. There's nothing else. Pop 6. 6 is completely processed. I've looked. Pop 5. There's nothing else for me to look at there. 5 has been completely processed. 4, all 4's edges have been considered. 4 has been completely processed. What about 3? Well, the claim was we already looked at 3. 3 had a back edge. Actually, 3, there was an edge 5, 3. That was already explored. From 3, from 2, pop this, 2. 2 is going to discover 7 now. So 7 goes on the stack. We start exploring from here. 7 goes to 1. Okay, discovered. 2 discovered. There's nothing else to be looked at. 7 is done. We go back to 5, to what? 2. 2 is now done. We go back to 1. 1, if we look at the outgoing edge, we discover 8. 8 goes on the stack. 8 has nothing else to discover. Go back, do 1. 1 is finished. Does everybody see how this tree came up? Okay? And why every edge here is either a tree edge or a back edge? Let's look at that. What about the edge 7, 1? Okay? We discovered 2 when we, 2 discovered 7. When we explored 7, 1 had already been discovered. That goes back to an ancestor. Does everybody kind of see that? Likewise, I guess, for 5. For 5, what was the back edge that we had? Well, there was an edge from 3 to 5. 3 had already been discovered. So this is going to become that back edge. Any questions about that? Okay. The interesting thing about DepthFirst Search is that on an undirected graph, every edge either goes to be a back edge or turns out that with a DepthFirst Search, all you can have are tree edges and back edges. Why can't we have this? Why can't it be that we have an edge that goes down to my grandchild in a DepthFirst search? If it's an undirected graph, why can't we have what we would call here a forward edge? An edge that is first encountered here and goes to my grandchild. Why not? Because when I was processing this edge, this vertex, I will eventually go through all of its children before. So this edge is presumably going to be discovered when I expand this vertex. Okay? And the direction on this edge is going to be going back to an ancestor, not here. If this vertex got discovered by, if this vertex got discovered in expanding that, what's it going to look like? It's going to look like a separate discovery, and then it's going to keep working on from here. So forward edges can't happen. Every edge is going to go back to an ancestor. Any questions about that? This requires convincing yourself of it. But the people see kind of what the reasoning is. The reasoning is just like on that DepthFirst Search thing. This edge, because I started this, and the moment I discovered this vertex, I focused my attention down here. The moment I discovered this vertex, I focused my attention down here. Here, I will expand all outgoing edges before I get back to working from that. That's why I will have a back edge and not a forward edge. Any questions about that? Okay. How many people sort of see why that is? How many people don't see anything? Okay. Any questions on anything? Okay. So again, a back edge is going to be what? A back edge is when an edge goes to a vertex that has been discovered but not fully processed. Why is that? Well, a back edge is going to an ancestor. Clearly my grandparent had to be discovered before I was born. Okay? But once I was born, I am going to be in a DepthFirst search. You're going to expand me. You interrupted what looking at the grandparents' neighborhood. Once it had a kid, I'm going to look at all of my outgoing children. And so if there is an edge that goes from, X to Y, okay, it's going to go up to an ancestor instead of down to a descendant. Any questions? DepthFirst search trees have this nice property that, again, every edge is either a tree edge or a back edge. If you have something that was a forward edge, it can't be. Because if there was an undirected graph, when we expanded vertex 4, we would have discovered this edge. And so it becomes a back edge. Any questions? Okay. And in a similar way, you can't have a cross edge. Could something like this happen in a DepthFirst search tree? Well, what would have happened? 1 would have begun. I would have discovered 2. I would have discovered 3. I would go back. I would discover 4. I would go back. I would process this edge. This edge is going, the tree is going to look like this. Okay? Because 5 would have been discovered when expanding 3. 2. Okay? And this is what the DepthFirst search tree would be. So no cross edges, only tree edges and back edges. Any questions? Okay. Before I go any further, let's look one more time at DepthFirst search and do a couple of things more. Kabunk. First, what is the running time of DepthFirst search? At the end of class last time, there was some debate and hubbub about what was the running time of DepthFirst search. Before I tried to convince you that it was n plus m. DepthFirst search is also n plus m. But I want you to look at it and to see why that is. What is the argument here? This kind of stuff is clearly O of 1. It's just doing a certain amount of little logic and bookkeeping. What happens if I roll a little further down? What's happening in the loop? That's the interesting thing. While p is equal to nil, okay, How many times is this loop going to go around? This is looking at the outgoing edges of vertex V. How many times is this loop going to go around? How many times? Yeah? The degree of V, right? If V has only one neighbor, it'll only go around once. If it goes around n neighbors, if it was it connected to everybody else, it could be n minus 1. But this is going to go around the degree of V times, right? Now where is the n coming from? Look at this program here. This is going to take order n time here. Where is the n? Does anybody see where the n is? Is there a loop that's going around n times? There was in DepthFirst Search, right? Where is the thing going around n times? Yeah? It is the recursive call. What is going on here? There is a recursive call for DepthFirst Search. What is this meaning? This is says, what's the story being? It is starting from a vertex V, and let's just try to see if I can get the DepthFirst Search on there too. Yeah, let's say, okay, boom. This DepthFirst Search call for a vertex V is going to take degree of V time and then call vertex Y, right? Every vertex in the graph is going to eventually get called to be the root of a DepthFirst Search tree under it. The time that vertex is going to process is going to be the degree of V, and we're doing that for every single edge, right? So what is the running time going to be? It's the sum as V goes from 1 to n of 1 plus the degree of V. The 1 is that order 1 time logic here. Okay, it's going to take constant time before the loop. This loop's going to go around the degree of V. What is this summation going to be? The sum of those ones is going to be n. The sums of the degrees of each vertex is going to be 2 times m. This is the running time of DepthFirst Search, order n plus m. Any questions? We're visiting every edge twice. We're visiting every vertex once. We're doing a constant amount of work every time we do these visits. The total effort is n plus m. Any questions about that? This is something you have to understand. Okay? Any questions? Okay? So DepthFirst Search also runs in linear time. Okay? It visits every edge exactly once, and every edge, gets processed once, and every vertex gets processed once. We could have done our bipartite coloring using DepthFirst Search instead of breadth-first search. The key point was that whenever we discovered a new vertex, it had to be colored differently than its parent. Okay, so we could have used DepthFirst Search for we could have used DepthFirst Search for bipartite coloring, but breadth-first search worked equally well. Any questions? Okay. In a few weeks, we are going to go talk about backtracking, which is a technique for doing exhaustive search of, exhaustive search of all possibilities, for solving things like the traveling salesman problem or something like that. Now, I'll talk about this when we get to backtracking. But when you get to backtracking, It turns out the idea of backtracking is exactly that of DepthFirst Search. You want to systematically visit all possibilities. DepthFirst Search systematically visits all possible vertices. Okay? And the way that backtracking works is going to be a recursive algorithm. It's going to mirror exactly what DepthFirst Search does. Okay? So file that away for now because you don't know what backtracking is. But understand that you'll see DepthFirst Search again in a different kind of guise. Okay? So we might as well try to figure it out now. Any questions? Okay. Any questions about breadth-first search or depth-first search? Okay. What is it? Okay, so I find breadth-first search and depth-first search dull and technical to talk about, because it's really just kind of a building block that you're building the other graph algorithms around. Recognizing these other graph algorithms, the more interesting graph algorithms are the ones that do something that you care about. Let's look at a couple of applications of depth-first search that does something on graph you might want to care about. Okay? How can we find a cycle in a graph? Let's say that here is a graph. Does everybody see that this graph has a cycle? A cycle is a set of vertices, a path of vertices that starts someplace and gets back to where you started from, right? How can we find a cycle in a graph? First of all, in an undirected graph, what graphs don't have cycles? Okay, what graphs don't have cycles? Yeah? Trees. So anything that is a non-tree, okay, any connected graph that's not a tree is going to have a cycle. How can we find that cycle? Okay, so the input now is I'm giving you the adjacency list of a graph, and the output is I want you to tell me the names of vertices that form a cycle. How can we do that? Okay. You know, something needs to organize it. What can we do to organize the edges of a graph? What happens if we do a depth-first search of a graph? What is going to happen? Starting from a vertex, there's eventually going to be a tree of discovery. Does everybody see that? And there's going to be other edges. What are the other edges? What are the properties that other edges in a depth-first search have to be? If they're not a tree edge, what is an edge? It's a what? It's a back edge. What does a back edge mean? Ka-chunk? It's an edge that goes to an ancestor. How does that tell us whether we have a cycle? Does everybody see that if you have a tree of discovery and you have a back edge, that back edge goes to an ancestor? Let's make this a little bit bigger, the tree. Boom. Okay? There is going to be a cycle formed. If you let's say I have a back edge, and this back edge is y, x. This is y. This is x. How can we find a cycle in the graph? Well, if we know that xy is a back edge, meaning it didn't discover a new vertex, then it's going to an ancestor. What could I do? I could start at y node here and walk up to my ancestor. Let me go back and do that again. Up to my parent, 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 until I find y, x. Okay, this I guess is supposed to be an x. Okay? What is the idea? A back edge is going to an ancestor. From myself, I could reach any ancestor by following the chain of parents. How do you get to your great-grandparent? You go to your parent, and then your parent's parent, which is your grandparent, and your grandparent's parent, which is your great-grandparent, right? So how do we get a cycle? The moment we have a back edge, namely, if we're processing an edge, xy, and the parent of y is not x, meaning that it's not just a little thing like this, but it goes to an early parent, okay? Then the claim is that there is going to be a cycle from, if we start from y and walk back until we hit vertex x, okay? Does everybody see that the layout of the edges, because of depth-first search, is going to enable us to find a cycle easily? Every cycle is defined by a back edge, okay, and the path in the tree that led to it. Any questions? What would a cycle look like in a breadth-first search tree? Let's go back to breadth-first search. You're saying, wait a second, breadth-first search was a good thing. I did my breadth-first search. I did my... Where would a cycle be? It's not going to be in the tree of discovery, right? It's going to have to involve some other edges. What do we know about the edge? The edge could be, okay, a cross edge. That's a cross edge, right? What would be a cycle? How would we find a cycle using a breadth-first search tree? Does anybody see what's happening? How would you do it? Yeah? Okay. I think what you maybe say is you would take a look at this and walk back on the ancestors of that. And walk back on the ancestors of that. Okay. That would define a cycle also. Right? But this is more complicated. Now you're walking back to two different ancestors. You also have to worry about the case where, what if the breadth-first search tree started here? The cycle that's being formed is not, going back to the root, but going back to the first ancestor in common. It's a lot messier to try to find a cycle in a breadth-first search tree. Does everybody see that we've got this beautiful property of, of how the depth-first search tree organizes edges? Everything is to a back edge, everything is either a tree edge or a back edge. Okay, and that makes it easy to find such a cycle. Any questions? What is the running time of this algorithm? Suppose I give you a graph with n vertices and m edges. What is the running time of using depth-first search to find the first cycle? Yeah? You say n plus m. Why do you say n plus m? If worst comes to worst, we're going to consider all the vertices. The moment we have a back edge, we're going to start walking up. How much time does it take to walk up the chain of ancestors? What's the worst amount of time it could take to walk up the chain of ancestors? What? N? Did I hear N? Okay. If my tree of discovery looked like this, it is possible this back edge would require me to walk up a tree of height n minus 1. Okay? But the moment I identify a back edge, then I can just walk up at most n vertices, and I've got that defining a cycle. Any questions about it? So it should be clear this can be done in one depth first search, so that's why you got n plus m, right? Is there a way that we could in fact actually stop? Notice that this algorithm will actually stop after only order n edges. Why is that? If we have n vertices, how many edges can be in the tree of discovery? How many tree edges can there be in a graph? If you have a graph on n vertices, how many tree edges can there be? What? N minus 1. Does everybody agree with that? If you have a tree on n vertices, it has n minus 1 vertices, edges in it. You learned that in AMS 301, or maybe even discrete math class, right? 213. 215, I guess. 215, okay? So what's the point? By the time you look at your nth edge, you are going to see a back edge. Does everybody see that? You can have at most n minus 1 edges discovering things. Every edge is either going to discover something or it's going to be a back edge. You are going to hit a back edge on the by the nth edge that you explore. Then if you just walk up and take the vertices, in fact, you could find the first cycle in order n time, regardless of how many edges there are on the graph. Okay? Do people see why that is? Every edge is either a tree edge or a back edge. The first back edge will define a cycle. There can be at most, they're going to be at only n minus 1 tree edges. So by the time you look at the nth edge, you've got yourself a cycle. Any questions? Yes? In order to find, actually if you want to read so once you have a back edge, you know it's not a tree. You know your graph has a cycle, right? And if you're happy to say you know that there's just a cycle, you don't have to walk up. If you want to actually see the cycle, then you have to actually walk up and find out what the vertices are on that path. Does that make sense? Any questions? Okay. So finding a cycle in a graph is easy and natural because DepthFirst Search did such a beautiful job laying out our graph. Any questions? Okay. Let's look at some other graph problems that are kind of interesting that you can do naturally with, with DepthFirst Search. Suppose you are a terrorist, and this was the phone network, and you wanted to blow up a station and cause mayhem. Which vertex would you blow up to cause the most mayhem? You see that? You've got this is a telecommunications network. Certain pairs of stations are wired to other ones. What vertex would you delete to cause the most mayhem? Does anyone? Which one? Okay. This is a test to see how good terrorists you make. Okay. Who here has an idea what they would want to blow up? Okay, I can't hear. The red one. What is important about blowing up the red one? Why is blowing up the red one a nice thing for a terrorist? What is the property of what happens when you blow up the red one? Does everybody see that there's now no way for the communications people on someone on blue to communicate to someone on green? Does everybody see that that one vertex disconnects the graph? And now there is no place to, no way for people in blue to get to green or green to get to blue. right? If you are a terrorist, okay, and you want to blow up something on the road network on Long Island, do you take out the, one end of the Triborough Bridge, or do you take out exit 50 on the Long Island Expressway? By taking out the bridge, you disconnect Long Island from civilization. Is that correct? Okay. And that is what an articulation vertex is. An articulation vertex is a vertex of a connected graph whose deletion disconnects the graph. It's the weakest point in a graph, the weakest point in a network. And if you are not a terrorist, but someone who's trying to build a reliable road network or a reliable communications network, you want to know where the weakest point in that graph is, right? Can anybody give me an algorithm to find out if there is a single point of failure in a graph? Based on what we've talked about so far, can anybody give me a simple algorithm to test whether there is a point of failure in a graph? Yes?
Try every single, like the delete every single vertex and do a BFS and then to see the one that gives you the most connected.
Okay. So you're saying what we're going to do is what? We're going to delete the edges coming out of this vertex, right? Then pick some other vertex and do either a breadth-first search or a depth-first search. If it's in one component, ka-chunk, 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 this is a depth-first search going on, doom, 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 it will visit every single vertex there, right? Same thing with a breadth-first search. You could try that vertex, oh look, that one didn't disconnect it. Let me now try deleting this vertex. Okay? What is the running time of this algorithm? Now here you do a depth-first search. It can't get to it. It's got two components. So this had to be a articulation vertex. What is the running time of your repeated delete a vertex and do a search algorithm? What is the running time of that? Does everybody see that the running time of that is n rounds of delete the neighbors of vertex I? How did we delete the neighbor of vertex I? Just blowing away the outgoing edges of vertex I. And also scanning the rest of my list to make sure that vertex I doesn't appear on it. Remember, in an adjacency list, edge ij will appear on the list of I and also the list of j. Okay? But certainly in linear time, I can blow away one vertex. I can then do a search to see if there's one component. I can then put that vertex back, okay, and try again. It should be clear that I could find an articulation vertex in n traversals of the graph. Okay? And that would give me something like n times n plus m. But there is a more clever way of doing this. Does everybody see this before we see something more clever? Does everybody see how that works? That's not clever. That's routine. That's good. Okay, nothing wrong with it. But that's something everybody should be able to do. What is a really clever way of doing this? What if we instead do a depth-first search starting from one vertex? Okay? What is going to happen? Every edge is going to be every edge is going to be either a tree edge, ka-chunk, 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 or a back edge, right? What is it that prevents an edge, a vertex, from disconnecting the graph? Does everybody see that if I have a cycle Okay? In a cycle, is there any vertex you can delete to disconnect it? No, a cycle is strong. You can blow away any vertex on a cycle. And it is going to, what you call it? You know, what's left is going to all be connected. What's the problem? A vertex is dangerous if it links cycles that are not otherwise linked. Does everybody see that? A vertex is dangerous if it goes to another component there that is not a cycle. Okay? But because the DepthFirst search did such a good, organized the edges in a clever way, every edge is either a tree edge or a back edge, right? If we have a back edge, okay, none of those vertices on the path in the tree are going to be candidate, are going to be candidate cut nodes, except for the one that is the highest up. Because that might be, you could end up with a world where it looks something like this. This node, if you delete it, would disconnect the graph. This node cannot. This node cannot. What should be clear is that if you're careful about, you know, if you do a DepthFirst search, one DepthFirst search from the root, if you're clever about how you think about things, you get the information on every node, you can tell whether it's a cut node by by things you encounter on one DepthFirst search. Can the root be an articulation vertex, the root of your DepthFirst search tree? Can that be an articulation vertex? Yes. If the root node has a degree greater than 1, what happened on the DepthFirst search? Ka-chunk, 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 ka-chunk. If the DepthFirst search root, if the root has a degree of 2 in the DepthFirst search tree, that root node is going to be a cut node, right? Just because of properties of DepthFirst search. And what I'd like to leave you with, and again, if you can look at the book for details, if you do the accounting, notice that a back edge saves some vertices from being possible cut nodes. By analyzing what happens as you sweep up with these back edges, you can identify the cut nodes on one pass. Okay? I want you to see that it's plausible, okay, and you can look at the book for details if you want. Any questions? Yes?
Does this mean the root is always an articulation vertex if it has 3, 2, or 3?
Say that again, I'm sorry.
Is the root always an articulation vertex?
Is the root always an articulation vertex? The answer is no. Why is it no? Well, first of all, realize that couldn't possibly be. If I had a graph that was a cycle, let's say my entire graph was a cycle, is any node here an articulation vertex? So there's no way that picking one to be a root can make it bad, right? But what happens if we do a DepthFirst search of this cycle? What's that DepthFirst search tree going to look like? If this is 1, 2, 3, 4, 5, what's going to happen? The tree's going to look like what? 1 discovers 2, 2 discovers 3, 3 discovers 4, 4 discovers 5, and there's a back edge. Do you see that in this tree, what is the tree? The tree is this. What is the tree degree of vertex 1? Does everybody see that it's only got its degree in the tree is only 1? If the degree was 2, what would happen? Well, that's something like this. If we did a depth-first search from here, what's going to happen? Ka-chunk, 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 ka-chunk. Then ka-chunk, 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 ka-chunk. Back here, now in the tree, it's got a degree of 2. That's the sign of problems. Is that clear? Any questions about that? Okay, so you should be aware of articulation vertices, have a kind of a sense that, wow, it's pretty amazing that this depth-first search organizes the edges. Everything is either a tree edge or a back edge, and that gives me great power. Any questions about that? Okay, fair enough. Let me try another important graph application of depth-first search on a problem on directed graphs. Okay? We say that a graph is a directed acyclic graph, also known as a DAG, directed acyclic graph, if it is a directed graph that has no cycles in it. Okay? So in this graph, which I realize is too small for you to see, they're directed edges. There is no way to walk legally on these one-way streets and get back to where you are. That means it has no directed cycles. A topological sort of a DAG is an ordering of the vertices such that all edges go from left to right. Let me show you an example that you can see. Okay, and I think that you'll understand this better there. DAGs are often used to represent precedence constraints. What is a precedence constraint that you have to deal with in your life? What did you have to do in order to take 373? Okay? Could you just walk into the university and say, I want to take 373? The answer is no. Why not? You had a prerequisite, right? What was that prerequisite? Hopefully you took 214. Could you have taken 214 when you walked into the university? No, you had to take 114. Does everybody agree? Does everybody see that scheduling and precedence constraints, you could imagine a world where every course at the university is a node, and there is an edge between course, let's say course 214 is required for 373. Does everybody kind of see that we can create a directed graph like that? Does the precedence constraint have cycles in it? What would it mean if we had a world where 114 was a prerequisite for 214, was a prerequisite for 373, was a prerequisite for 114? Suppose we had a cycle in that order. What would happen? Yeah? You would never get your degree, right? Does everybody see that? I'd never have to teach any students in 373 because nobody would have the prerequisites for it. Okay? So this is why we carefully designed the curriculum to not have cycles in it. Does everybody agree with that? Because of that, there's a sequence of courses you can take. You can take 114, and then take 214, and then take 373, right? That linear order of courses that you could take it without getting a constraint is called the topological sort. Okay? Any questions about that? Any kind of precedent world has these, wherever there's certain things have to be, jobs have to be done before certain other jobs. Unless it's a DAG, you're going to get into problems. Here's a good example from getting dressed in the morning. Okay? Do I have to put on my underwear before I put on my pants? Yes. Do I have to put on my shoes before I put on my pants? No, I have to put on my pants before I put on my shoes. Does everybody see that? What is a legal order? Do you see what these precedents are? What is a legal order to getting dressed? Okay? I could start off by putting on my socks. What's the second thing I can put on? Anyone want to help me get dressed this morning? What else can I put on? Now. Somebody. What? Pants? Okay, I can't put on pants. What did you say? I didn't see pants. I can't put on my pants. Why not? Actually, I had to have my undershorts first, but now I can put my undershorts on. Now, once I put my undershorts on, can I put on my pants? According to you, yes. Now I can put on my pants. Once I put on my pants, can I now put on my shoes? Now I can put on my shoes. According to this, what else can I put on? I could put on a shirt. I could put on my watch. Once my shirt's on, maybe I can put on my tie. Once I have my tie on and my shirt and pants are on, I can put on the belt. Once that's done, I can put on my jacket. Okay? Any questions about that? Does everybody see that there is a precedence constraint here? Does everybody see that there are multiple orderings that can be used? It's not just one, okay? There are many, many different orderings that are possible here. Does everybody see that I can put on my watch at any given moment of the day? I could wake up and put on my watch. I could wait till I put on my underwear and put on my watch. There are many, many possible orderings. If I have n jobs to do, what are the most possible orderings? Can anyone give me a network of constraints where there's most possible orderings? Well, if there were no edges between anything, how many possible orderings are there? Suppose you take a bunch of courses which have no prerequisites among themselves. How many possible sequences of courses would work? N factorial, any arrangement would. What is the least possible number of orderings? 1. And how do I enforce that? If I have a path, ka-chunk, 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 there is only one possible way to do those jobs, satisfying the orderings. Any questions about it? So the problem of topological sort is, how do I find a legal way of doing this? Okay? Any questions? Let me give you a quick algorithm since we're running out of class, but then we'll give a more sophisticated one next class. What if I find I claim that in a DAG, every vertex, there has to be at least one vertex that has in degree 0. Does everybody agree that this one has in degree 0? So I'm going to put the one of in degree 0 first, and then delete the outgoing edges from this. If I had a DAG before, if I do this, am I creating any cycles? No, I'm only making it easier because I'm deleting edges, right? Now any vertex that is in degree 0, what vertices here are in degree 0? Can anyone give me a vertex that's right now got in degree 0? Someone. Someone with a voice. What? Watch. I could do the watch. Okay. Is there anything else of in degree 0? Yeah? Shorts? Let me delete that and delete